All right, we're going to go ahead and discuss the integrated rate laws for first, second, and zeroth order reactions. So when I say integrated rate laws, what we're going to be doing is looking at the rate law. And of course, the rate law is going to relate reaction rate to concentration. Unfortunately, for first, second order reactions, the concentration of the reactants are constantly changing. Thus, the rate is going to be constantly changing. So if we were to want to know or investigate how concentration is changing over time, we need to do some manipulations to our rate laws, and that's where we're going to come up with these integrated rate laws. All right, so that could be quite handy. Let's say you take a medicine and you want to know how long that drug is going to be active in your body. All right, so we need to figure out how long that drug will be in a particular concentration in your body for a certain amount of time. All right, so what we're going to be doing first is taking the rate laws for the first, second, and zeroth order reactions, and we're going to manipulate them mathematically using calculus. Now, calculus is not a prerequisite for this course, so I'm going to be doing the appropriate calculus for us, so don't worry about that. You'll never have to derive these equations on your own in this course, so don't worry about the calculus. Don't let it scare you, but we're going to get the integrated rate law out of this. So why don't we go ahead and take a look first at the first order integrated rate law. All right, so we're going to have a reaction of A going to P. All right, so we have our reactant A and our product P, and we can go ahead and write our rate law for this first order reaction. Now, I'm claiming it's first order, so of course I know it's going to be first order. All right, so if I'm going to write the rate law for this reaction, all right, that is going to be K times the concentration of A. All right, I also know that the rate of consumption of A is going to be equal to delta concentration of A over delta time. And since this is a reactant, I need my negative sign there. All right, so I have the rate law and the rate of consumption for my component A. All right, I can do a little bit of rearrangement to this to make it a little more familiar to those of you who've taken calculus. The delta sign in mathematics rather than chemistry is listed as a small d. All right, so when you go over to the math department, the delta just changes to a d. All right, so we have something that looks like this. All right, so all I've done is translated the end of that rate equation to a more mathematically familiar, or an equation that looks more familiar to a mathematician. All right, and I'm going to set it equal to the rate law. All right, the next step is going to be actually rearranging. All right, so I'm going to move dt and my concentrations of A around. All right, again, this is part of the calculus derivation process, so no need to panic. All right, so I've done a little bit of algebraic rearrangement. So going back, I moved this guy over there, and I moved that guy over there. And there we go. All right, so what I can do now is integrate this equation. So integration is given by the little squiggly S symbol, and Isaac Newton came up with that actually. All right, and we're going to have two limits. We're going to go out to concentration at time t, and we're going to begin at the concentration at time 0, all right? And I'm going to move my negative sign out here. So what I'll have is dA over A, and I'm going to set that equal to this integral. So I got to integrate both sides. So I'm going to go from the time t back to my time 0, and I've got k dt. All right. So now through calculus, and if you've taken Calc 2 essentially, you will be familiar with integrals and integration. But what's going to pop out of this integration is going to be ln, the natural log of at over a0, and that's going to be set equal to minus kt. And I rearranged the negative sign a little bit. All right, so here is our integrated rate law. All right, I'm going to rewrite this on the next slide. And going back and remembering that if we have a natural log with a over b, that's equal to the ln of a minus the ln of b. And that can be quite handy. So let's go ahead and split that out. So we have the ln of at minus the ln of a0 equals minus kt. And then I'm going to go ahead and move my ln of a0 over to the other side. So I have the ln of at equals minus kt plus the ln of a0. This is the really nice part of the integrated rate law. All right, so I'm going to put that in red. This thing is great because it has a very familiar form of y, m, x, and b. All right, so the initial concentration of a0 is actually a constant, right? You know that value. You start the reaction with this known value at a0. Again, that's the concentration of A at the beginning of the reaction. So you know that, all right? K over here is also a constant. That's the rate constant, and that's going to be our slope, all right, of the reaction. X, of course, is our horizontal axis, and Y is our vertical axis. So if we look here, X is a variable, right? And y is also going to be a variable, okay? What I mean by that is that the concentration of A at a particular time is going to vary depending on what that time is. So this is a linear line, and if you notice, it has a negative slope. So a plot of ln of at versus t is going to give us a straight line or linear line with a negative slope. All right, so let's go ahead and recap that here. So I have the ln of at equals minus kt plus ln a0. All right. So when I plot this, on the y-axis, I'm going to have the ln. I need a little more room here. ln of at versus t. I'm going to have a negative line. All right, and right here is an important point. This is our what's called the y-intercept, and that's going to be equal to the ln of a0. Okay, that is our y-intercept. The rise over run, or with the slope of this line, is equal to minus k. All right. Of course, the slope is negative. K cannot be negative, so you need to account for that with that negative sign out in front of k. All right? So this is very powerful because now what we can do is we can make a linear relationship of concentration of AT, specifically the ln of the concentration of A at time t versus t. All right? So let's go ahead and look at a mathematical example how to do this. All right, so I'm going to have a chemical reaction of taking sulfuryl chloride, SO2Cl2, and if I heat this up it will decompose into sulfur dioxide gas and chlorine gas. Pretty nasty stuff. All right. So what we can do is we've got a rate constant for this reaction. At a particular temperature is 2.9 times 10 to the minus 4 inverse seconds. So the inverse seconds tells us we're definitely dealing with a first order reaction. All right. They're saying if we carry out the reaction at this temperature and the initial concentration of sulfuryl chloride is equal to 0.0225 molar, what will the concentration be after 865 seconds? All right. So they're giving us the rate constant, and they're telling us it's a first order reaction, and we have an initial concentration. So now they're asking us for a final concentration. So this is the beauty of the integrated rate law. All right. We're just going to plug in our variables and look for what we need to solve for, and then that's going to, the first order integrated rate law is going to give us everything we need. All right. So let's go ahead and write out the integrated rate law for a first order reaction and write down what variables we were given. We were given the rate constant, K. That was equal to 2.90 times 10 to the minus 4th inverse seconds, minus 4th. We were given A0. That is what? The initial concentration of the sulfuryl chloride. That was given to us at 0.0225 molar. We were also given a time, T. Right? T is 865 seconds. All right, notice our rate constant is in inverse seconds, so our time needs to be in seconds. All right? What do we need to find? We need to find the concentration of sulfuryl chloride at time T, which happens to be 865 seconds. So what we need to solve for is AT. All right. So we need to do a little bit of rearranging of this equation. All right. Actually, no, we don't. We just need to go ahead and plug in our variables and then solve for AT at the end by taking an exponential of it. All right. So let's go ahead and get to work here. We know that the ln of AT, which is our concentration after time t, is minus K. So K was 2.90 times 10 to the minus 4th inverse seconds. T was 865 seconds plus ln of 225 molar. All right. All right, so I'm going to start simplifying this equation. So the ln of AT, I'm going to go ahead and multiply K and T together. So 2.9 10 to the minus 4th times 865 gives me, and I have to remember to keep my negative sign out there, 0.251. All right, and then I'm going to add this to the natural log of 0.0225. So I'm going to go ahead and take the natural log of 0.0225, and I get negative 3.79. So I'm simply going to add these two numbers together. So I have negative 0.251 1 plus negative 3.79, and I get a negative 4.04. So my ln of AT is equal to that. All right, so how do I now solve for AT? Of course, I need to take the exponential. Right, recall that the ln of A equals x. If you want to solve for A, you need to take e to the x. All right, so I'm on my calculator. Make sure you can do this as well. You have to be comfortable with your natural log and especially your exponential function on here. And when I take the exponential of that, I get 0.0176 molar. All right. Now, you always want to go back and double check. The concentration should decrease over time. All right. What was our initial concentration? 0.0225. And it's gone down to 0.0176. So it indeed did increase. So that sounds good to me. All right. So that's how you use the first order integrated rate law to solve for a concentration after a particular amount of time has gone by. All right. So don't get lost in the derivation. I will give you these equations. All right. On an exam situation, and that one right there, you'll get it. Okay. You'll be responsible for using that equation. All right. Okay. Now I want to move on to second order integrated rate law. All right. So again, we're going to go A to P. And we know that the rate of a second order reaction would have this rate law. All right. How did I get to that rate law? I know it's second order. Okay. And if it's second order, that means we get an exponent of 2 here. All right. So a rate law is always K, and then you just work through the reactants and make sure you get their orders in with the correct exponents. Okay. We also know that that change in A, any rate is measured in the consumption of A per unit time, so that's negative dA over dt. So I can fix this now. All right, so I've set the rate of consumption equal to the rate law, which I can totally do anytime. All right, and this just happens to be a rate law for a second order equation. So that's going to change the integration laws a little bit, or quite a bit, to be honest. All right, so after taking a little bit of a rearrangement here, so that's what my equation can be rearranged to. And now I'm going to integrate it via calculus. And out pops the following equation after a little bit of rearrangement. Again, I don't want you to get lost in this calculus here, in algebra, honestly. It's more important that we have an equation that you need to learn how to use. All right? So it looks quite a bit different, okay? That's fine. This is now our second order integrated rate law. Okay? So what's different about this? Well, we now have no natural logs, all right? But we have these fractional representations of AT and A0, all right, and we have our old friend K and T. So this actually is fantastic because we see our old friends again. Y equals mx plus b. Sweet. So we got a linear line here. Again, now what is it going to look like? What is on the x-axis? Time again. Cool. What is on the y-axis? 1 over at. What is our slope? Wow, it's positive this time. Okay, so we have a positive slope. Looks good. All right. But something's a little bit different here. All right. It's going to be our y-intercept. Our y-intercept is actually going to be down here, and it's going to be non-zero. All right, 2 reasons. If we have 1 over A0, okay, let's say our initial concentration is 10, and our final concentration is 2. I'm just making these numbers up. All right, 1 over A naught would be, as the equation states, 1 over 10, okay, or 0.1. 1 over AT would be 1 over 2, or 0.5. So that's weird, all right? So what we have is the reciprocals. And the reciprocals, as the numbers get smaller, the reciprocals get larger, all right? So while it looks like the concentration is increasing over time, pardon me, that's K, is our slope. Trying to cram this at the bottom of the screen, and iPad does not like it. All right, so that is my y-intercept right there, which is equal to 1 over A naught. Now, back to this line, it looks like the concentration is increasing over time. That's not the case. What's happening is the concentration is decreasing, therefore their reciprocal values are increasing, all right? So as I demonstrated up there, as that concentration goes down, the reciprocal values increase, so it's kind of counterintuitive, all right? But again, we have a slope that is positive in this case, which is quite a bit different than what we saw in the plot for the first order reaction. All right, what I'd like to look at now is the 0 order integrated rate law. So if we go back to our simple reaction of A going to P, all right, we can go ahead and write that our rate is equal to K, concentration of A, to the 0th power, all right? That's the definition of a rate law for 0th order if we have our single reactant, all right? And the rate of consumption, as always, has been delta A over delta T. Now, since it's being consumed, we need that negative sign. So as we've seen before, if we go ahead and set these 2 equations equal to each other, after a little bit of rearrangement, we can have the following expression made. And using calculus, we can integrate that equation, and what we will be getting out of that will be the 0th order integrated rate law, which looks like the following. So there she is. All right. And what do we notice about this? I'll move it on to the next page. No natural logs again, that's nice. Well, we see our friends again, Y, M, X, and B. And there's nothing too tricky about this plot, all right? On the y-axis, I'm going to have AT. On the x-axis, I'm going to have T. and I'm going to have my intercept. So I don't have to worry about reciprocals. My concentration will be the highest at the initial point, and then it's going to decrease, as you'd expect, linearly with a negative slope. All right, my slope is equal to minus k. All right, so that is the makeup of our plots. All right, so we have our three integrated rate laws for first, second, and zeroth order, and I've shown you the plots for each one of those. All right, and in lab, what we'll be doing very soon is we'll be plotting data on Excel, and we'll be trying to figure out whether the reaction is first, second, or zeroth order. All right, and the way you can do that very quickly, if you have a table of data, all right, let's say we have something like A, all right, the concentration, and we can do ln of A, 1 over A, and then just A. Oh, we already have that, silly. All right. And then what we can do is we can look at the time that was monitored. All right. So we can have time 0, and we can have a concentration of A measured. All right. Let's say that just happens to be, 4 or 3 or whatever. All right. Then we would take the ln of 3 and plug it in there. And I'm not going to do that right now. And then we would put this over here. Okay. And then we could do another time. Let's take time 5 seconds. Now the concentration is 2. All right, it's going down. So then we'd have the ln of 2 here, and then 1 over 2 here. All right, and you put this in an Excel spreadsheet, and then you can make 3 different plots. You can make A versus T, ln of A versus T, and then 1 over A versus T. And whichever one comes out to be the most linear is going to be the most likely order of reaction, all right? So let's say this one comes out and looks like this, all right? And this guy looks like this, and then this guy makes a nice, beautiful straight line, all right? Then you can tell from an experimentation, since this one had a linear response, that is consistent with second order reaction order, all right? These do not have linear responses in this case, so they wouldn't work. All right, more details on that to come in our lab coming up, but this video just will serve as our review of the 3 integrated rate laws, all right, and how to use them. All right, so be looking for some homework practice on these. Thank you very much.